Hola a todos. It is an honor to get to introduce our speaker today. My name is Leslie Olesko. I'm an investigator here at the today I get to introduce one of my intellectual heroes. This is Tanya Smith. She is visiting Burgos from Griffith University in Brisbane, Australia. She is currently an Australian Research Council Future Fellow, and she has followed quite the international career path. She has been a professor at Harvard University in the United States and was a researcher at the Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany, with a short stint that she spent at the University of California, Berkeley, before she headed off to Australia. As you will see in this talk, Tanya's research is truly an impressive and inspirational mix of paleoanthropology, oral biology, and chemistry. She has innovated a range of methods and approaches to study how teeth form and the information that can be gained from variation in chemical signatures that are absorbed during that formation. So Tanya also has written a book aimed at the general public that shares the wonders of the study of teeth. It is called Tales Teeth Tell, which is a mouthful. This was published by MIT Press in 2018, and I highly, highly recommend it. If after you have heard her talk, you definitely want to read the book. There are little postcard advertisements of this, so please grab one to remember the name. So please help me in welcoming Tanya to CENIEH.
Thank you very much for that warm introduction, Leslie. Thank you, everyone, for attending today. And hello to anyone joining us on the live stream. It's really an honor and a privilege to join you today. And my goal is to hopefully excite you in one of multiple directions about the different types of evidence that we can pull from teeth regarding our ancient and current development, evolution, and behavior. So I'm going to just start with a tiny bit more introduction for those of you who are perhaps unfamiliar with the subject of biological anthropology. This is the area that Leslie and I are both specialists in. And in fact, my original draw to biological anthropology was not teeth. It was actually our closest living relatives, the great apes. I was intrigued by the similarities in their behavior and the complexities of the way they navigate the landscapes that they're in, and in fact went to graduate school not to study teeth, but in fact to study their behavior. It wasn't until about 15 years later that I managed to get to Africa and actually see them in the wild. And this individual bud you'll see later on in the talk. So I wanted to just give a little context to my early career and say that for those of you who are early career researchers yourselves, you never know where your research will bring you. When I got to graduate school, I met a very important person who became my doctoral advisor in my second year, and that was Lawrence Martin. And he was a specialist of tooth structure, enamel thickness, and someone who was starting to explore the fine-scale development of teeth. And I never knew until then that you could actually build a career out of studying the tiny microscopic anatomy you find within teeth. But Lawrence quickly introduced me to Meev Leakey and gave me an opportunity to run his lab and work on fossils that had been sectioned. And that opened up an entirely new direction for me. So I'm going to share with you some of those directions today in a very broad way. And I hope that we can have some question and answers about maybe some of the finer details that might pique your curiosity. So we'll start with how teeth can help us better understand development. And I will give you 10 tales teeth tell over this talk. We'll start with the first and the one that's most central to my research, which is that teeth have tiny timelines locked inside them. And you can see these in the images here, which are actually images of a fossil ape, a 9-million-year-old fossil ape that has diagonal lines running across it, which are actually formed every 9 days, as well as tiny little light and dark boxes you can see in this slide, which are actually 24-hour rhythms or daily rhythms in the growth of this fossil primate. So many of you have learned about tree rings. You're familiar with cutting a tree and counting the annual rhythms within the trunk, the growing edges of the trunk. But in fact, we have a much finer system of time recording inside our own bodies. And we know this because we're able to do microscopic studies. And so we, in my laboratory currently in Australia and in other laboratories around the world, actually make physical cuts of teeth, like this chimpanzee molar you can see here in full and in half in the slide. And then we produce tiny thin sections or microscopic slides that we then put under various types of light microscopy to be able to enhance and see these microscopic growth lines. So you may wonder, well, how do we know they're actually 24-hour rhythms? What kind of evidence would establish that there's this fundamental clock ticking? And this was a question that I worked on during my PhD, as have others, and we were able to use a labeling method, a biomarking method, to be able to actually establish the external time of formation and relate that to these internal structures. So what you're seeing here on the left is an image of a monkey tooth enamel, cut again and polished and put under a microscope, with a couple of experimental markers. You may see an XO and an M. Those are actually biomarkers. They're fluorochromes that had been given to this monkey in life, 7 days apart. And then the individual was sacrificed later, not for my research, but for a different study decades earlier. And we were able to actually relate those known time markers, those 7-day apart time markers, to tiny little timelines inside. And we were able to establish in this instance there were 7 light and dark bands between those 2 biomarkers. Again, just confirming that there are these 24-hour rhythms at play in tooth enamel. We've done similar work on tooth dentine. You're seeing here, this is actually a rodent incisor on the lower right. And there are these lead acetate biomarkers, which were, again, injections given to the developing rodent in this instance. And here they were given 5 days apart, and you can actually see these faint bands. There are 5 light and dark bands between these 2 biomarkers. See, this is the kind of foundational experimental work which has been done by teams in Japan, in the US, in Europe, to really prove that without a doubt we know there are fundamental daily rhythms at play in a range of vertebrates. There are finer lines and even supra-daily lines. I won't get into the details now, but just so you know, this again is this foundational system of time. And that starts even before you're born. And we know this, which is really a boon for dental detectives because you can see these lines both on the inside and the outside at a scale, again, finer than the ridges on your fingertip. So we know that these processes start before you're born because we actually can detect birth. We can find the physiological transition that occurs in our bodies as a slight shift in the chemistry and the structure within teeth. So we all have in our first molars a birth certificate. We know where day 0 is in terms of our early life history. And you can see that here is this dark accentuated line highlighted with blue running, again, just above the dentine horn. And in humans, it tends to be about 3 weeks of formation prior to birth on average, maybe a couple weeks more or less, depending on whether you're born early or late. But your first molars record your birth, as do all of your deciduous or your baby teeth. So you have a permanent signature again of that important marker. In my book, I talk about this individual, which is a deciduous tooth from a child that I was the first tooth I sectioned in my new laboratory when I started at Harvard. And I was incredibly excited to be able to produce a thin section and to try to find the birth line in this individual, which is illustrated here with this white arrow. This is a magnification of this region here in the early part of the incisor. And in this instance, I was actually excited because I knew where I was on that day. This was my friend's son, and I was her doula. So I was there with her, cheering her on as she delivered this beautiful baby boy. And I was able to actually then, 7 years later, find his birth in his tooth, which was very gratifying. We can also apply this to fossil hominins, to other primates. And in fact, we have. This is an instance of a really enigmatic Neanderthal individual with a very large brain. This is the very first hominin fossil ever discovered, the Angers Neanderthal, in the winter of 1829 to 1830. At the time, they didn't understand it was a Neanderthal, but they found this seemingly large crania with a set of teeth here. They made an estimate of how old they thought it would be based on modern human standards. And then almost 200 years later, we were able to use synchrotron imaging to find the birth line in this Neanderthal. And you can see that magnified here. And I'll tell you a little bit more about how that helps us understand the evolution of human development in a few moments. But the point here is that birth is this foundational thing, which is found in all mammals and other vertebrates. And so to be able to recognize this gives us just incredible insight, not only into gestation, but also into the speed of later development. And finally, in terms of development, I want to just highlight some work that we've been doing on of other events that are manifest in teeth. So birth is the foundational event. We all have birth in our teeth. We're all here today. But many of us also have postnatal events, which reflect things that happen to us in early life. And in order to establish this, I've been very fortunate to work on a group of monkeys from a facility that have records of the individual's stress and health histories. And so I've been working for about 15 years now on these monkey teeth. I create the thin sections, and I work on mapping these developmental defects, or these accentuated lines, and I give them ages relative to birth. So in each instance, I'm able to find the birth line in the monkey teeth. And then I find postnatal stresses, and I make estimates of when those stresses were relative to birth. So these are ages and days. And then in the younger individuals, I'm actually able to go all the way from the enamel into the dentine, and I capture the last formation there and estimate the death of the individual. And so then when I put the medical records up against the stress lines, I can see what's going on, what's causing these disruptions in tooth enamel. And in this monkey, this instance, there were a number of things that I was able to resolve effectively in a blind manner. So at 25 days of age, the individual was moved from one enclosure to another. That led to a very fine stress line in its teeth. Unfortunately, at several months of age, the individual developed a leg abscess and got very unwell, and it had to be hospitalized, along with, it separated from its mother at that point, and that led to a very strong developmental stress that lasted for, over a week. Later, the individual again had another hospitalization. The poor individual had an amputation. So there were a number of really stressful events that happened to this individual, and they were all captured in these growth disruptions within a couple days of the actual events that were recorded. And then finally, I was able to test my estimate of the individual's age against the records, and I was within 1 day. So that's a kind of accuracy that is rare in my experience, but it really points to the faithful record that we can extract of an individual's history, whether it's a subtle stress due to an unfamiliar environment, being separated from a mother, being sick, having a traumatic injury, or ultimately not surviving, that we have this incredible record of development preserved in teeth. So that then leads me on to my next series of tales, building on the foundational understanding of tooth development and the way that histology can help us kind of probe fine-scale details in individuals' lives. I'm going to move to kind of evolutionary tales, and I'll start with a really broad one. We'll zoom out from the microscopy. I now live in Australia, which many of you may think of sharks immediately. We do have, unfortunately, shark attacks in Australia. And sharks are kind of an interesting foil for this talk because they have continually replacing teeth, which you can see in this image here. Just these rows lined up, ready to go. So when you just snap one off, boom, you can just move another one into place and, keep being that scary predator that we're all aware of. We don't have that ability to just move a new tooth into place when we lose one. Certainly, dentists would love to be able to come up with a way to be able to replace teeth, but there's no way because we have only a single set of tooth replacements. And so this phenomenon unites us all as mammals, and we know this relates to our life history. We know, for example, we're born unable to fend for ourselves, and so we are dependent on our mother's milk for some period of time. In some mammals, that may be 4 days, and other mammals, it may be 8 years. And during that period, we have what we call a milk dentition or a deciduous dentition. And then that is replaced with our permanent dentition in order for us to have our own ability to process food on our own. So that replacement unifies us. And we can see in the fossil record, when tooth replacement became just a single set of replacement teeth as opposed to this continuous replacement as one of these defining transitions from a reptile-like ancestor to a mammalian ancestor. Another key evolutionary transition relates to the development of different types of teeth. many of you are familiar with in this group, the morphology really helps us better understand the function. And you can see here in this example of a tree shrew and in a lemur, the differentiation in the different parts of the dental arcade gives us clues as to what individuals were doing, whether they were gouging trees with their prognathic incisors, which is rather unusual from our perspective, or slicing things with very sharp carnassial teeth. We've got the ability to recognize across the mammalian, groups the differences that these highly specialized teeth allow. More efficient mastication, effectively, instead of just being like a shark, kind of indiscriminately taking a few bites and then swallowing something and very inefficiently processing. We are united in that more specialized dentition, which again is a reflection of our evolutionary history as primates and mammals more broadly. Teeth are built to last. We sort of take for granted that we're all walking around with fossils in our mouth, 96% mineral, effectively, so well calcified that we can recover even the tiniest bits of protein locked in the matrix of tooth enamel, millions of years later. It's just incredible to think about that protective matrix that allows teeth to be recovered from millions of years ago. This is an example here of the fossil orangutan collection in Leiden. It always impresses me to visit that museum where you can go and see thousands and thousands of fossil orangutan teeth, almost none of which have tooth roots, in fact, because the roots were being eaten by porcupines that were collecting them and dragging them into caves. When you ask the curators, how many living orangutans do you have in their museum, they have far fewer living orangutans available for study than they do fossil orangutans. We have this incredible representation of the past, which is highly tooth dependent. And that's really true when you think about the hominin fossil record, and we think about our prehistory over the last 6 million years. We're often showing pictures of skeletons, hominin skeletons, but you think there's only tens of skeletons, and you think about crania, skulls, just maybe hundreds of skulls. But when you think about the representation of teeth, we have thousands and thousands of teeth. They are the greatest type of evidence that we have for our prehistory. And when we think about humans and Homo sapiens specifically, so much of what we know about the dispersal of Homo sapiens throughout Eurasia, throughout down into Australia, the region where I currently call home, is actually based on isolated teeth in some instances. That's the only information that we have that says, yeah, we were here, because we have these characteristic tooth crowns with certain morphologies, which are very obvious. Obviously now we've got some more sophisticated techniques, paleoproteomics and ancient genomics, to be able to test the affinities of these teeth, but until quite recently, again, teeth were the best marker I think we had for understanding our dispersal through time. Obviously, all the archaeologists would argue with me immediately and say, no, we have stone tools and we can say something about who's producing stone tools. But in terms of biological anthropology and the study that we can have on the actual fossil record itself, teeth are the most well-represented element. I want to turn now to my last tale related to evolution, and this is a topic that I worked on while I lived and worked in Europe a number of years ago, which really relates to our own childhood and how we then integrate an understanding of tooth formation to probe questions about our evolution. Many of you are familiar with some of the famous juveniles in the fossil record, the Dakika child being one of the most well-publicized in the last 20 years. The Narcotomy individual, again, another developing individual, and then Neanderthals. We have over 100 juvenile Neanderthals in the fossil record. And these growing individuals present an opportunity for us to ask questions about how human development may have changed over evolutionary time, how human-like we were in the past, or perhaps how ape-like we were. So all of these fossils that I'm showing you have now been studied from a microstructure analysis perspective. People have used an understanding of dental development to be able to get in there and ask questions about how they grew up. And I've been really lucky to be able to employ a synchrotron to be able to ask questions about the evolution of human development, along with my collaborator, Paul Taffarot, who's been in Grenoble, France for over 20 years now, developing technologies to be able to probe those tiny timelines without cutting any fossils, which is a key to be able to get access to some of these key individuals in the past. So I'll show you an example of the type of information we can get from the synchrotron with this video animation that we'll play now for you. And this is a fossil individual. It's an example of an early Homo sapiens from Israel. This is a COFSA 5 individual. And you can see here just a photograph, zooming in on where the synchrotron imaging was performed. So this is the mandible, and here's a kind of what we call a low-resolution scan of the mandible, showing you the permanent first molar along with the deciduous teeth. And then in the bone, you obviously can see the developing permanent teeth. What the synchrotron can allow us to do, though, is to go up with much higher resolution to be able to resolve the fine microstructural details on the outsides of the teeth. So here you're seeing paracomata, or growth lines, running horizontally on the outside of this first molar, and this is with a medium resolution. And then we can peel through the tooth and with even higher resolution pull out the fundamental microscopic structure of the tooth enamel. So these are enamel prisms. You're looking at them end-on, circular enamel prisms, and longitudinally. And what you can see as you peel through this 1 millimeter by 1 millimeter square are these tiny little daily growth lines. You can see each day of formation of this tooth preserved virtually. Again, we didn't have to cut this fossil to resolve this. So Paul and I, starting about almost 20 years ago now, integrated these different technologies with, with this sort of eye to resolving how these fossils were growing. So we'll move on to the next slide now. We'll just stop the video, and I'll bring you back to the presentation to tell you a little bit about what we first learned, thank you, about the earliest juvenile from our own species that we have in the fossil record. This was the Jebel Arud individual, currently dated to 300,000 years, from Morocco. And we, at the first instance, just took a tiny piece of incisor enamel to Grenoble and imaged that with a synchrotron. And we were really trying to get one key piece of developmental information out of it. And that's the number of tiny daily lines in between these longer period rhythms. And so after 3 different experiments, we were able to get what we called the enamel periodicity from this incisor chip and use that to infer the time of formation of the incisor, the canine, and the first molar. And that gave us access then to that individual's age. And so we could have an independent measure of its true age, not just its calcification status, which is how usually people were working on fossil hominins without having an independent clock. And if you put this fossil hominin into a sample of modern humans, which are shown in these green circles here, if you put the individual from Morocco into the sample, it falls within a pool of modern humans. And what I'm contrasting here is the actual age of the individual, or that histological age, with what you would expect based on modern human calcification standards. So if we took our own radiographs in this room as kids and we plotted our age against what the calcification status was, you get a general sense of how human growth and development is over the life course or over the childhood period. And again, that fossil from Morocco fell right within the modern human range, as did the COFSA 5 individual, which you can see here. What's different, in fact, are Neanderthals. And so here's our Angers individual from Belgium, which ended up being 3 years of age, despite modern human standards predicting it should be older, 4. We had other fossils, Neanderthals. We had individuals from Le Moustier, from Krapina. We had a Belgian fossil from Skladina. So we looked at a range of Neanderthal fossils from different parts of Europe, as well as different geological ages. And what we found was, on average, Neanderthals were growing their teeth faster than they would if they were following a modern human pattern of growth and development. And so this technology allowed us to look at a number of individuals, both from our own species and other species, and to be able to put those into the context of what modern standards are like. So we argued again that this was really distinctive, that we don't see that kind of long, slow, delayed dental development in other hominins. And this technology also allowed us to ask other questions about growth and development in the past. So a couple years ago, we employed the same approach to work out the age of the Dakika individual, this famous fossil child. And we have, in this instance, a full skull and skeleton as well, so that we could ask other questions about how does its brain development compare, for example, or how does its skeletal development compare. Now that we had a concrete age, we knew the individual was 2.4 years of age when it died, we could benchmark that against modern humans, as well as African apes and other hominins. And no surprise, Dakika turns out to be much more like a chimpanzee growth trajectory. These are chimps in red, little circles here, and you can see that they are distinct from the green circles of humans. They are also distinct from the Neanderthals, and it's falling really with Australopiths, so other both South African and a couple East African individuals that we were able to age using the same technology to show, again, that there's a real distinction between the earlier hominins in the fossil record and the later members of the genus Homo. Far, far greater gap than we see, for example, between Neanderthals and modern humans. Okay, so people ask why. Why would modern humans slow down their development? What is the benefit to having a long, slow childhood? Why delay your reproduction? And I can't answer that question. I can only speculate or share other people's speculations. But I put a couple of hints in this slide. People argue that having a long, slow childhood allows more time for that beautiful brain to develop, for the learning of complex behaviors, for the learning of complex technologies. When we think about our children today, with phones and computers and the sort of really long period of neural rewiring that's going on into our 20s, that we have this much more complicated and sophisticated society, potentially as a consequence of having this longer period before we begin worrying about reproducing and provisioning our own offspring. I'm not sure if that's true. It's one theory. It's interesting. But we certainly stand out from the other hominins in that regard. So the final set of tales I'll just take you through briefly are related to our behavior, and some folks in this room know quite a lot about this. We know, for example, that teeth help us better understand the evolution of the human diet. And in the US at least, the paleo diet was really in vogue 15, 20 years ago, and everybody was speculating about what ancient humans were eating and how that should inform today's diets. And there were ideas about certain foods being not popular in the past. And in fact, when you take scrapings of dental calculus, that tartar that our dentists are commonly removing from our teeth, you find all kinds of things in ancient hominins' diets, ranging from cooked starches, which wouldn't be allowed on the paleo diet, to pollen, to residual pigments from paints that had been used in the past. We were finding this incredible diversity of foods and a variety of things that were in the oral cavity, which are getting locked inside layer upon layer of mineralized plaque, effectively. So this is a really growing field of really reconstructing aspects of human diet as well as other curious behaviors from dental gunk. Another key area of research is this idea of how teeth have not only allowed us to process food, but to process other objects in our environment. And there was an influential theory for a while that teeth started to reduce because tools became more sophisticated, and so we didn't need to rely on our teeth to process food as much as we could cut and ultimately heat and cook things. But in a sense, we came back around to realizing our teeth themselves are great tools. And this is a Neanderthal, classic image of a Neanderthal with the type of wear that cannot be explained by occlusion. This is not simply tooth-on-tooth contact. And so this is often modeled as being, the result of using teeth as a third hand, effectively, and grasping things between your teeth that you could then process. And I love this example of the idea of processing meat, potentially, or defleshing animal skins with a sharp object, because we actually find evidence of sloppy cutting on teeth. It turns out that teeth, particularly from Neanderthals, as well as early modern humans, often show really large striations on their anterior surfaces, which are not due to chewing. So it looks like somebody was kind of sloppy when they were holding something between their teeth, every once in a while chipping the teeth. And not only were they chipping them, they were chipping them preferentially as if they were right-handed. So we have this evidence of what we call a paramasticatory behavior, or a non-chewing related function in teeth that we can recognize from both the unusual wear, but as well the unusual striations that we find on teeth. And then some of the most evocative examples of human behavior relate to art and symbolism. Some of you in the room may have markers of your personal adornment on your skin in the form of tattoos. In the past, we knew that people used teeth to express their identities through modification, filing, notching, chipping. And this was afforded to individuals we think of different social status. So we have evidence of a sort of social distinction in the past because of these very elaborate formations that we find on teeth, as well as elaborate inlay, which we find particularly in Central America, in certain cultures in Central America. And I know now tooth bling is popular, but very few people are actually having deep holes drilled into the fronts of their teeth to be able to put a semi-precious stone with an organic glue. That would be very painful to do. So again, we have this symbol of social status in the form of tooth inlay and different forms of filing that we find in the past, the recent past. And then finally, for those of you who are thinking about modification of teeth, and the discomfort we may experience when we go to the dentist, we know that we have, an ancient history of tooth modification for palliative care, for helping with pain. And unfortunately, tooth decay and cavities are something we see not just in our own species, but we see even in chimpanzees and in other non-human primates. So we know that tooth decay has been a problem in the past. We see this in contemporary populations, even hunter-gatherers, which isn't something that we thought, typically we would consider caries or, a disease of modern civilization. But we do have evidence for the development of tooth pathology and the treatment going back at least 14,000 years. And if you're curious about, how ubiquitous is this across the primate order, it turns out that non-human primates also manipulate their oral environment. One of the classic stories of this is actually from a captive colony of chimpanzees in the US. It's a story of two juveniles, Bella and Bandit. And so these are young chimpanzees who started out in a grooming relationship. And so Bella is grooming Bandit. And after she started grooming his fur, she just got curious about his mouth. And she started, feeling around in his mouth, and she found a loose tooth, a baby tooth. And so she started wiggling and got really curious about it. And eventually she got a stick and decided to try to work out Bandit's tooth. Can you imagine a chimpanzee tolerating another chimpanzee, taking a stick? It was such a sort of an interesting thing that other individuals came and watched Bella as she ultimately knocked out Bandit's tooth with a stick and kept that for quite a while until the keepers eventually were able to retrieve both the tooth and the stick. But this idea that the oral cavity is somehow only in humans' awareness is not true. We know that primates can floss their teeth, or sometimes even in captive environments, they'll take bristles out of brooms and they'll use them to knock things out between their teeth. So, we have this sort of, again, this very common primate pattern of being aware of what's going on in our mouths. And I'll just close with one final tale. Because here's Bandit. This is what Bandit would look like. In fact, this isn't Bandit. This is my friend Bud that I was with in Uganda. But I don't know how comfortable many of us would be reaching in with a stick and trying to knock out one of these teeth. It would be pretty, I think, overwhelming for a chimpanzee. But I want to just close by sharing something more contemporary in terms of the work that I've been doing. And this is something I feel really excited by: the idea that we can use an understanding of tooth chemistry to pull out ancient climate records and even understand something about the seasonality of our reproduction. And this is based on analyses of isotopic chemistry using thin sections of teeth that we're probing with an ion microprobe to be able to sample every single week in that ancient climate, and then put that against time and age to understand somebody's early life history in terms of when it was summer or winter, or when it was raining or not raining in an arid period. And so we were able to actually take a Neanderthal tooth and work out its first 2.8 years of life in terms of climate cycles, and plot the oxygen isotopes through time in relation to the individual's nursing history, which we established through another chemical technique, as well as its exposure to lead in its environment, and even illness. And so here's the history of a 125,000-year-old Neanderthal from southeast France. Looking at all of this information together, we were able to establish it was born in the springtime At 9 months of age, it experienced the coldest part of its first winter when it was exposed to lead, mysteriously. And then it lived through another summer. It got very sick during the coldest time of its next winter, and then it was exposed to lead again, mysteriously, during that winter or early spring. And then finally, we were able to establish that it stopped nursing. It was weaned in the autumn at 2.5 years of age, and then that tooth stopped forming the enamel at 2.8 years, so the record was ended at that point. But this is just the example of the kind of complex paleobiology that you can pull out if you understand something about tooth development and tooth chemistry and some of the geological systems at play that influence our environments. So I want to say muchas gracias to my friend Leslia and to the Tied to Teeth group for hosting me today, and I look forward to taking questions. Thank you.
Thank you so much for that awesome talk. I know I'm a little biased since I studied teeth, but I thought that so many interesting things, and I definitely have a lot of questions, but I think I should let the audience go first. Does anyone else have a question that I could? Yeah.
Please.
Of course, I'm also biased, but it's not about that. It was a wonderful talk. It was beautifully the content, but also the way you exposed it was really, really amazing. So I have a lot of questions too, but I don't want to monopolize. But I was going to ask you, the neonatal line, is it recorded as a stress event too? Or is it different from the other lines?
The sort of light microscope image that I showed you, it looks very similar to the kind of stresses that happen after birth. It's a slight change in terms of the transmission of light, so often it looks like a brown line. The enamel prisms look slightly different, so there's a slight shift in terms of the crystalline structure, but it's also characterized by a little bit of a chemical shift. So in some instances we can pick up a hypocalcification. Okay. So there's actually both a chemical and a structural change.
And then it is amazing all the precision, you say, of the things and the vents you can really get at the microstructure of the enamel. Yeah. So I know comparatively we cannot say the same at all, but I just want to know what's your understanding of how gross or non-useful or reliable or unreliable is to use the timing of dental development to infer changes in development. So we know the time and the timing, and so in fossils that we did not apply synchrotron, we did with the pattern of timing. What do you think about it as a marker of development?
I think it's a very useful external way of knowing, where somebody got to if they died before they finished forming their teeth. So, I said in the past you only had human standards to apply. So you would say, okay, well, the individual didn't erupt its third molar, so it must be less than 18 years of age. But that's not a very, both independent. It's not independent of humans, but it's also not very precise. So we, for example, with the Dakika individual or even the Neracotomy individual, to be able to say we know that was a 2.4-year-old child means then that we can say, okay, skeletally, is it at the 2.4-year mark? No, it's not, right? Or cranially, is it at that mark? So whether you like this for life history reconstruction proper, i.e. predicting weaning, predicting age at first reproduction, predicting total lifespan, that's debatable. But for just simply being able to then look at ontogenetic achievement through time, microstructure is the best tool we have. Does that make sense?
Yes, but for example, what about using the relative development of the posterior dentition eruption as an indicator of not childhood, but maybe something related as childhood? Would that work as an orientation or not?
Yeah, I think in a broad sense it does. And Holly Smith just wrote a lovely paper looking at dental development related to seasonality. And I think she made a really convincing point that, across mammals more broadly, there's a good relationship there between the eruption of the first permanent molar and that transition to adult diet, and that actually has a relationship to the way that animals are reproducing. So most mammals, they go through that transition after about a year from gestation, the beginning of gestation, to that eruption. So there's this ecological limit. It's good to have your babies before a full year, because then you can effectively time that to the best time in terms of the resources in your environment. So yeah, being able to look at a fossil, effectively anything, and say, okay, we have no permanent teeth. That individual was probably still dependent. Or we have some permanent teeth, that individual had probably transitioned. So that gives us a kind of general sense of where that individual fits in terms of its, I would say, maybe not formal life history, but its general relationship to its environment and degree of independence.
Okay. And finally,
Yeah, no problem.
I know you were talking about I would say this, in your interpretation, this unique pattern of slow growth modern humans have.
Yeah.
And we also see like the picture about Australopithecus and early representatives, which are like in the other extreme. So in that context, how would you put Neanderthal? So it's not that slow, but would you still say that it's close one to the other? Do you really see differences? Can we infer that they have a sort of delayed growth or sort of early childhood?
Yes, they are delayed relative to Australopithecines, for sure. There's kind of a continuum where you have a rapid ape-like in the early hominins, and you do start to see that movement in the genus Homo. I mean, unsurprisingly related to brain size and transformation of locomotion. So we start to see a shift towards the modern condition. Neanderthals are very close. Any individual Neanderthal may be almost like us. On average, as you look at a number of Neanderthals, I think there's a slight difference, but it's not a gross difference. It's not the same as an Australopith. Does that make sense?
Yeah, but if someone would ask you, like, did Neanderthals have childhood? Would you say yes or no?
Sure.
Yeah.
I mean, chimps have childhood. You know, I mean, animals have a period of dependence. Did they have like a long adolescence, maybe? Did they have a late reproduction? Yeah, probably relative, again, to earlier hominins. They would have shown something much more like us. Was it exactly 18 years? I don't think so. But was it close? Yeah.
Okay. Thank you.
Thanks. And well, actually, I guess not everybody is a full adult by 18, and some are full adults before then. So there's a lot of variation in that. Also, if you're listening, if you're watching online, please, if you have a question, please put it in the chat, and we'll get that. So more questions over here. And then if you could pass it back to Arthur after.
Thanks, CENIEH. I mean, I know that you can hear me, but maybe I'll live it better.
They're going to bring another microphone. They're bringing a second microphone down for you. I can also repeat the question if you want to ask it. It's up to you.
Okay, sure. So actually the point is, I just know a little bit about taxonomy. You focus most of your work in animals.
Yeah.
I know that there's a huge lab, which is dentin.
Yes.
So what information can be extracted from dentin?
Yes.
Hola. So I repeat the question.
Yeah.
So actually, I would like to know which is your thought, which are your thoughts regarding dentin
Yes.
compared to an animal?
Yes.
Very radicular band, equivalent of Prochimara.
Yes.
Okay, so your thoughts about how information can be extracted from them, because actually it takes longer than an animal.
Yes. Dentin has all the same rhythms that an animal has, and in some instances, it can be very easy to recognize time in dentin. Unfortunately, it's very rare for the entirety of dentin formation to be readable from histology in the same way that an animal can be. And that relates to a few things. The geometry of a dentin formation or root formation is very difficult to capture in a single slice. It's curved, so you think about trying to catch a plane that is actually a curve, and you only can get part of that in any one slice. We've had luck with synchrotron virtual histology to be able to capture dentin formation, and I believe there should be a paper out today on the Demonisi juvenile showing its age at death using dentin increments. So it can be done. It's quite rare, but there are all the same rhythms. It's difficult to say the daily rhythms are as easy in the dentin because they're parallel to the longer period rhythms. So in an animal, they're not perpendicular. They're at an angle to one another. So it's easier to see different timelines in an animal. It's a little bit harder in dentin. But Those lines are all there, and we did a study, oh goodness, almost 20 years ago, showing periradicular bands do have the same time dependency as paracomata do. But again, they tend to be covered over with cementum, so they're much harder to study because that glue that holds the root in the bone obscures those timelines on fully erupted teeth. Yeah. I think Arthur had a question. Yes. No.
Do we hear in the microphone?
No,
Okay. So you're clearly showing evidence that there is variation in the timing of development for teeth.
Yes.
But, and this is a biased question also, so we know that the brain, the face, the dentition, all are completely integrated in terms of development. And do you or do we have any evidence that the selection of this variation in timing have been done uniquely on the teeth, or maybe the selection of a variation of timing have been done on the brain development, and as are they integrated, both are slowed down or speed up? Do we have any ideas on that?
I mean, we might have ideas. I'm not sure if we have any evidence. I often think that, you know, beyond the transition that happens after mother's milk stops being provided, which is a key transition. You must have a functioning adult, beginning of a dentition to be able to process food. Like, that's non-negotiable. If you don't have any teeth, you know, you're not going to survive. That, I think there's selection on the timing of that and the teeth that are available. But beyond that, I can't see why in the same way, because if you're transitioning onto an adult diet and you can process it pretty well, but you still don't have your third molars, I'm not sure why selection would be acting to worry about the timing of those. I think that's more of a latent effect that relates to the overall development of the rest of the system, whether it's the brain that's driving it. You think about when we achieve maximum, you know, brain size, it's much earlier than the posterior molars are forming anyhow. So I think, you know, again, after that initial diet transition, I don't think that teeth are what's driving the timing. And again, I mean, just to give a plug to Holly Smith, she's shown that they're related. So, you know, you tend to have a suite of developmental transitions that happen, but I don't think it's as tightly correlated, certainly. Yeah.
Great. So we don't have any online questions. So I'm going to ask my question.
Please.
So I think I'll ask the most fun one.
Okay.
So if you could have 2 teeth.
Oh, boy. Yes.
One primate individual.
Oh.
From any time point in all of evolutionary history, what would you want? Which teeth and what kind of primate? And why?
That's a really hard question. I mean, I'm always interested in looking at first molars because they have the birth line and they are recording the nursing transition often. So that's my favorite tooth class. You know, do I have a favorite type of hominin or primate that I would want to study? I feel already that I've been so fortunate to study them. Like, I was able to work on Afropithecus, which was so exciting because it was the first thick enameled hominoid and showed the earliest evidence of an ape-like pattern of dental development. So I would have picked that, but I had the great fortune to work on it. I mean, you know, I'd love to spend some time with some Ardipithecus teeth. That would be really cool to see what kind of developmental pattern you have there. We don't know very much about the internal microstructure. You know, we have worked on, you know, other Australopiths, but certainly we still have some questions about, you know, is it really just a sort of ape-like pattern, or are there some subtle differences we know with apes today? So that would be something interesting to me.
Well, I do have to say that all of us here who study teeth, we definitely think you have lived the dream. So it's wonderful to see that you think the same thing. Yes. Appreciative of all the amazing work that you've done. And thank you so much for sharing all of that with us today. It's been an honor having you here.
Thank you. Muchas gracias.